Okay, class. So we are now on the last unit operation for part 1 of the review for unit operations. And this topic is about drying. So before we go to the design of the dryer, let's go into the specific definitions or things fundamental to drying. So drying refers to the removal of a relatively small amount of water from any given material. So mostly these materials are solids. Now water is usually removed as vapor by air. So water is removed from the solid in the form of a gas. And the thing that removes it from the material is air. Now, drying may also refer to the removal of other organic liquids such as benzene from solids. Now, usually, this drying procedure is the last step of the series of unit operations in a manufacturing process. This is carried out so that in terms of the life of the solid that is actually packaged, it will be greatly improved. Because we know for one that if a solid has a moisture content which is higher than the one that will preserve its shelf life or for its intended shelf life, then that particular solid will deteriorate. So as such, it's very important that it is dried prior to packaging. Now, there are two types of moisture that we need to know regarding the concept of drying. So we have this what we call bound moisture and the free moisture. So the bound moisture is the water retained so that it exerts a vapor pressure less than that of the free water at the same temperature. Such water may be retained in small capillaries, adsorbed on surfaces, or as solution in cell walls. So that's bound moisture. It remains in the matrix of the solvent, or of the solid rather, or of the material. What about free moisture? This is water which is in excess of the equilibrium moisture content. It's in excess of equilibrium moisture content. Now, those are the two types of moisture. Now, in terms of the humidity, because we will be dealing with humidity in designing our dryers later on, we need to define what humidity is. Although we will study in detail the use of the psychrometric chart in the topic of humidification and dehumidification. Now, for now, we will content ourselves with the definition first of humidity. So, when we speak of humidity, that's the mass of water per unit mass of dry air, or the amount of water that dry air contains. And its formula is expressed in terms of the partial pressure of the vapor divided by the total pressure minus the partial pressure of the vapor. That's the humidity per unit mass of dry air. What about humidity of saturated air, which is represented as H sub O? The subscript O meaning it's saturated. This is the humidity of air when it is saturated with water vapor, meaning it holds the maximum amount of vapor that it contains in a given condition. The air then is in equilibrium with the water at that given temperature and pressure. So as to the measure of the water that air contains at this particular condition of saturation is what we call as the humidity of saturated air. As to percentage humidity, we get the percentage of the humidity, the actual humidity that we have defined in here in terms of its saturation value. So percentage humidity is H over H sub O times 100. Now, again, this is humidity of saturated air and this is humidity of air and this is percentage humidity. What about percent relative humidity? And it's represented by R. This is actually the partial pressure of water vapor in air divided by the vapor pressure of water at the same temperature. What is the partial pressure of water vapor exerted in air over its vapor pressure at the same temperature, and we multiply it by 100. That is percent relative humidity. What is worth noting here that in this measure of humidity, we are dealing with pressure. Whereas in here, we're really dealing with content, water content. But in here, we're dealing with pressure. Now, there is this thing we call humid volume. Actually, in terms of the units that it has, it is volume per unit mass. If you look closely, it's just the reciprocal of the density. So, how do we define this one? It is the volume of unit mass of dry air. So, take note, unit mass of dry air and its associated vapor. Then, under ideal conditions at atmospheric pressure where temperature is expressed in Kelvin, the humid volume of an air-water mixture is given by this formula. In this formula, you could see that you have to substitute the temperature in Kelvin and the humidity of air for you to be able to get the reciprocal of the air water mixture, reciprocal of the density of the air water mixture, which is its humid volume. Now, we also have what we call the time of drying, and when we calculate for the time of drying, we calculate for the drying time at falling rate period and at constant rate period. So, as to the constant rate period, since it's constant, that time there is represented as T sub C, as you can see here, and the formula is also expressed in terms of omega and omega. Omega 1 is the initial water content and omega C is the critical moisture content of the air water mixture or water vapor mixture. R sub C is the rate of drying per unit area, which is equal to simply the product of the mass and the difference between the critical moisture content and the equilibrium moisture content. These two, I think, will be defined in the next slide. So this would be the time for constant rate period. As for the time for the falling rate period, you will still have the appearance of the W's, but in here you will also need to add the WE, and you have the M and the A. So anyway, the A also appears in the formula on top. So for the falling rate period, it's 1 over MA, where M is the mass of the material and W is the total moisture content. Moisture content measured at that particular time in which you are to determine the drying time, or that the time that it took for your material to reach that particular amount of, for your rather air to have that particular amount of moisture on it. So that's your falling rate period. And by the way, I've mentioned air. This is something to do rather class with the solids that is being dry already. It has nothing to do with air. So in here, we're determining the drying time for a solid at constant rate period. And this is the drying time for the solid or for the material at falling rate period. The drying time total will be the sum of these two. So this total moisture content I mentioned a while ago is the total moisture content of your material measured at any particular time, not of air. I stand corrected. Now, so the total drying time is the sum of the time for the constant rate period and the time for the falling rate period. And for the free moisture content is the moisture content at any time minus the equilibrium moisture content. So these are but formulas, very simple formulas that we can get from Jean Couplets regarding the concept of drying. Now our dryers are divided into two types or two groups. We have the continuous dryers and we have the batch dryers. So I leave for you to look at into the types of dryers under this particular cluster, let's say continuous dryers, because we have contact continuous dryers, meaning there's the transfer of heat is via conduction. We have convective type of continuous dryers, wherein the transfer of heat is via movement of fluids, and the other one in here, which is the specialized one. And as to the type of material that is being handled, they are further classified in here. So if you will have to use a continuous contact type dryer for a particulate solid, this will be the type of dryer for you to use. So this is how you should interpret the diagram. For a continuous contact type dryer handling particulate or solid feed, then these are the types of dryer available for you to use. If it's continuous convectives, wherein the process is through dispersion and your feed is particulate feed, this would be the particular type of dryer that you will be using. So the clustering is in terms of operation. So this one is continuous, the other one is batch. And again, the two clustering is divided into what type of heat transfer is being used. So contact is conductive, convective for the middle, and for other types you have the third column. And then further classified in terms of the type of feed that that particular dryer is going to process. So please look at this. Probably this may come across, you may come across this in a form of a concept type question later on. Now, so as for the category of the drying processes, so we classify them as, this should be number 3. Heat is added by direct contact with heated air, or it could be vacuum drying. The removal of water proceeds more rapidly at low pressure, and heat is added indirectly by contact with a metal wall or by radiation. In the case of vacuum drying, the heat is being transferred to the solid that needs to be dried via radiation. Okay, here in the first one, heat is added by direct contact. So this is more of conductive, convective type of drying. And we have the last, the specialized type of dryer, which is the freeze drying. Now, water here is sublimed from the frozen material. Now, this is your shaft or tray dryers. This was discussed. You just read on the specific application of this tray or shaft dryers. I'm not sure if this condensed form of notes for tray or shaft dryers will be the same or as condensed as what is available in your handbook. So it really helps if you're going to read them as well. You can retain some of the readings later on that will help you time in looking in your handbook on a particular concept that may be asked during the board exam. So for tray dryers, these are more things for you to read. Now for tunnel dryers, you have a series of trays or trolleys that is moved slowly through a long tunnel. And as such, the term tunnel. This one is tray, so as such it has tray or shelves. For drum dryers, so you have a drum or a cylindrical rotating drum. Now consists of one or more, this is or class, heated metal rolls on the outside of which a thin layer of liquid is evaporated to dryness. Your dried solid is scraped off the rolls as they slowly revolve. So cylindrical drums that are revolving. For spray dryers, this may combine the function of an evaporator, a crystallizer, and a dryer, all in one equipment. So this is worth noting. And you add to that a size reduction unit and a classifier. It reduces the size and it classifies the product as to the sizes of the dispensed solids. So evaporator, crystallizer, dryer, and a size reduction unit and classifier. So in here, your feed is in the form of slurry or liquid solution. It is dispersed into a stream of hot gas in the form of a mist of fine droplets. As to the illustration of this specific dryers, I have included it then in your heat and mass transfer slides in your course. So just refer to the specific illustrations for this. Now, very short drying time. So I think this is the only dryer that mentions that the drying time is short, which permits drying of highly heat-sensitive materials and the production of solid or hollow spherical particles. So that's special about spray dryers. Now, this is more to read on the spray dryer, so please read it. Now, we also have the rotary dryer. So, similar to the drum dryer, it is also involving a cylindrical shell that is revolving. It could be horizontal or slightly inclined. So, the wet feed enters on one end of the cylinder and the dry material is discharged from the other. So, heating here is through direct contact of a gas. Whereas in the case of the drum dryer, it's not direct contact with the gas, but rather you have the concentrated solution of highly soluble materials which are being concentrated through the evaporation of a thin layer of liquid. So there's a evaporation of a thin layer of liquid. Now, this is not suitable. The drum dryer is not suitable for solutions of salts with limited solubility, and it's not suitable for slurries and abrasive solids. Take note of this. Now, let's look at the rotary. So, desirable for material that tends to dust and used for salt, sugar, and all kinds of granular and crystalline materials. So, if the other one cannot process salt, the drum dryer, although they are the same in terms of physical design, this one can, the rotary dryer. So focus on each dryer in terms of what feed they can handle, and most especially on the type of drying method that is being used. Now this is more for the rotary dryer type of problem. So this is, I think, a problem that was given to you in HMT, and actually the solution of this was already given to you then. So I don't want to give you something that was already given to you then. So just review. As for the methods of heating for a rotary dryer, you have direct heating or indirect heating. So direct heating, where the hot gases or air pass through the material in the dryer, and indirect heating, where the material is in an inner shell heated externally by hot gases. So alternatively, steam. So in this case, steam may be fed to a series of tubes inside the shell of the dryer. That is in the case of indirect heating. Main problems concerning design of dryers are normally focused on rotary types or the drum types dryer. And if you're going to look at review materials on drying, board exam on drying, kalabanan, the problem or most of the problem is giving you a problem on the rotary dryer. So in terms of the heat transfer in the rotary type dryer, Coulson gives us this particular formula, still patterned after the UA delta T, convective type of heat transfer. So it's the parameters or the variables that appear here are defined below. So you have A as the area of contact between the particles and the gas per unit volume of the dryer. So this could have been a simple capital letter A, but since we are provided with area of contact between the particles per unit volume of the gas in the dryer, then we have this small letter A, and it will be multiplied by the volume of the dryer, because the gas that is used in drying the material is assumed to be having a volume equal to the dryer volume also. Now the delta T is the mean temperature difference between the gas and the material. As to the length, so this is the heat transfer area. As to the length, this is the length of a particular rotary dryer. It needs the rate of heat transfer, it needs the diameter, and it needs the air mass velocity, the G prime. I have a very comprehensive sample problem of this given in your heat and mass subject then. Please go through again your notes because the process is very long. So if we intend to review that one particular problem alone, might use more than half of our review time already. Nonetheless, again, you can encounter here the delta T lug mean temperature difference. The same formula that was discussed a while ago under heat exchanger. Okay? Now, in the case of adiabatic dryers, so that's for the rotary dryer. In the case of adiabatic dryers, we have this number of transfer units formula that is only available in Colson. The formula uses the inlet and outlet temperature of air, represented here by TA1 and TA2, and the wet bulb temperature of air. So check again because there's a sample problem on this, on the wet bulb temperature and the given wet bulb temperature, or how we get the wet bulb temperature given the condition of the air that is used for drying. Now, McCabe does not give any problem on drying specifically concentrated on packed beds. Only John Kuplis discusses this in detail. And this is the true circulation drying in packed beds. The drying here occurs this way. So the drying gas passes upward or downward through a bed of wet granular solids. So packed bed consisting of wet granular solids, and air is still your drying medium. So it either passes up the bed or below, passes upward or downward. So it's either going up or going down as long as it passes through the bed. So often here the granular solids are arranged on a screen so that the gas are free to pass through the screen and through the open spaces or voids between the solid particles. Now with this type of dryer, you have this formula. So the amount of water removed from the bed by the gas is given by the formula R equal to G times H sub 2 minus H sub 1. Now, R is the rate of kilogram waters removed per hour per square meter. Cross-section of that particular bed, which is simply a screen having the solids on top. The G is the gas mass velocity, or specifically the dry gas mass velocity, the G. H2 and H1 are representing the humidity of air, initial and final, after the drying proceeds. Now, this one allows you to solve the amount of water removed in a packed bed drying. What about if the design asks you to determine how thick should a bed be? Or how thick should your packed beds be? The thickness by John Kuplis is represented by letter Z, and it is solved using this particular empirical formula, and the unit stipulated here should be followed. So C sub S is the humid heat of air water vapor mixture. Specific heat is humid heat. Humid heat here is just the specific heat of air water vapor mixture. Then we have the H as usual as the heat transfer coefficient. A, the surface area of the solids expressed per unit volume of the bed. T sub W again is still wet bulb temperature of solids. T sub 1 is inlet gas temperature, and T sub 2 outlet gas temperature. This refers to the temperature of the air mixture. Okay. So that's it for the thickness of the bed. For the time, still talking about the packed bed, for the time for constant rate period and falling rate period, we have a heavy formula provided by John Kuplis for this. That way we can determine the overall drying time in packed beds. And it's empirical because there has a lot of things here that we need to take into consideration first before we can apply it on this particular formula. So there's this note applicable only for fine particles of diameters 3 to 19 mm and shallow beds about 10 to 65 mm thick. So at most your bed should only be around 6.5 centimeters thick. For these two formulas for the time for constant rate period and falling rate period to be used. Otherwise, we cannot use them anymore if it's below 10 and beyond 65. Now, you see in this formula, the H, you have the H, that would be this H here. So, the H here has two sets of formula SI and English for both sets, which has differing range of values for the product of dP, GT, and mu. Now, the dP is the diameter of the particle, the GT is the total mass transfer rate, and mu viscosity. For greater than 350, this should be the formula that you should use. For less than 350, this should be the formula for you to use. There's no pressure as to recalling all this formula. All you have to do is make sure that you know where you can find an equivalent of this in the handbook. If it's not available in the handbook, there's no assurance that it will not be given though in the board exam, because there's a lot of formulas from sample problems that are not found in handbook. And normally graduates will able to answer those problems because they simply memorize the answers on those sample problems. But nonetheless, these are formulas for packed bed drying. Considering the solving first for the H, that should be substituted in here, in this formula. Now the A are using this formula here. For particles that are spherical, this should be the formula for the A. Which A is that? Means the small a's that you see here. Okay, so A's, and you have the epsilon here, dP. Okay, diameter of the particles. This is how we determine this. dP, diameter of the particles when they are not in the form of spheres. So if they are cylindrical, you are to convert them into this particular value so that the cylindrical particles now in shape is converted into spherical formula, because the formula here only uses diameter for spherical particles. This one, tipulon, bula. If it's not bula, if it's cylindrical, the formula should be converted to one that is equivalent if it is in the form of a sphere. Now, I have again here inserted problems on drying that you may be able to use. I think I inserted around 5 that will help or add more to what you already learned as to how we're going to process drying problems and even design dryers based on the principles discussed. So I will I will rather post in Canvas later the problem set for this part of Unit Ops. I will just will take some rest, and then I will proceed on recording for part 2, which I will also be uploading in a little while.